Welcome back, everybody. Welcome back to the HackerWay track. If you've joined us from one of the other tracks, very pleased to see you here. We are making a move now from the process of mobile design, which I hope you all found fascinating, into some of the topics around hardcore mobile engineering at Facebook. Obviously, we have made a transition over the last 12 to 18 months to really think of ourselves as being a mobile company first. And that's meant that we've had to think of ourselves as being a mobile engineering company first. And that's brought with it a whole host of challenges, both organizationally and technically. In both this session and the next session, you're going to hear how we've made that journey, both on Android, on iOS, and in our build and release processes. As I said at the beginning, I have one job, and that's to get off stage as quickly as possible. So I'm going to leave you in the very capable hands of Tom Alison.
Thanks, James. Let's get started. So my name's Tom Alison. I manage some of our product engineering teams at Facebook. I've been with Facebook for almost 4 years, and every day I have the privilege of working with some really talented teams building mobile products. Some of the teams I work with build products for our main apps. So, for example, we have a team called the Core Experiences team. They're responsible for the overall primary navigation of our apps on Android and iOS and the mobile web, the look and feel of the Chrome, and the core newsfeed experiences, which is one of our most popular Facebook products used by millions of people every day across the world. I also get to work with some teams that are building new products and standalone apps. I've worked on Facebook Home, I've worked with the Paper team, and we have some engineering teams that are building some new standalone apps that hopefully we'll be able to share with you guys in the future. And so what we're going to do in this talk is actually have 2 talks about how we build mobile products at Facebook. The first talk is going to be about how we've scaled broadly on Android, both in terms of the number of engineers that we've grown working on the code base and the number of people in the world that are using that product, and some of the challenges that it's introduced. Next, we're going to shift gears, and we're going to go deep. And we're going to talk about a small team and a very ambitious design challenge that they had to tackle in order to create our latest standalone app, Paper, for iOS. Before I introduce our first speaker, I want to set a little bit of context about what we mean by scale in our mobile engineering orgs. When we started building mobile products a few years ago, we had a really small, centralized mobile engineering team, a handful of engineers on each interface. We had a scaling challenge very quickly. We had lots of engineers and product engineering teams building for the web, and we couldn't keep up with the amount of features that we needed to port over to mobile. And so what we did is we started developing out mobile expertise in our product engineering teams. For example, the Photos team started owning the Photos features in our mobile apps. And that worked okay for a while, but today we're a mobile-first company. People expect that all of your features are going to work as good on mobile as they do on the web, and in fact, I'd say people expect that the mobile product is going to be better at this point. And so we had to scale again. Today at Facebook, we don't have a mobile engineering team anymore. Mobile engineering is in all of our product engineering teams. This is something that we have embraced as an engineering company across the board. And many of our infrastructure engineering teams are critical to contributing to the mobile code base as well. This has been an interesting challenge because we've scaled the mobile code base from a handful of engineers to dozens to well north of 100 contributing very actively every day. And we need to ship a high-quality app every 4 weeks. And so that's an interesting thing that we'll talk about. Then, of course, there's the number of people using our products, which brings in another dimension of scale. We recently talked about how we have over 1 billion monthly active mobile users across our Facebook products. And like a lot of you have probably seen in your products, a lot of growth that we've seen has been on Android, which introduces its own set of challenges. And so what I want to show is actually some data from a third-party research company called IDC about where Android is going. What you see on this chart is the growth, the projected growth in internet-connected Android devices through 2018. And IDC projects that in 2018 we'll have almost 1.5 billion internet-connected Android devices in the world. And that's excluding China. The thing that's almost more important for me is the mix shift that's happening. Most of the growth in Android is going to be in emerging markets. In 2013, more than half of these devices were in the developed world. By 2018, more than 70% of devices running Android are going to be in emerging markets. What that means is that when we're building mobile products, we need to create great experiences, not just for the devices that we all carry around in our pockets, but for the entire world. We need to understand how to diagnose a crash that's happening on a Galaxy Ace in Indonesia, or a problem that's happening because of flaky connectivity in Kenya. And so to talk about how we've learned from some of those things in our Facebook from Android app, I'd like to introduce Jenny.
Thank you, Tom. So my name is Jenny, and I'm an Android engineer at Facebook. I've been at Facebook for about 2.5 years, and in this time I've been focusing on a bunch of our mobile products. Amongst them are the main Facebook Android app, as well as the Facebook Home project. Let's talk more about Facebook, mobile at Facebook. As Tom mentioned, we currently have over 1 billion mobile monthly active users, and this number is growing every single day. We ship really fast. In fact, every month we release an APK out packed with hundreds of code changes built by dozens of engineering teams. If we compare the app that we released today with the first one we released back in 2009, you'll notice a lot of changes. Our app today is much more performant, and it has a lot of features that back then were only available in the desktop web version. One unique thing about building for mobile is the low tolerance for error. What do I mean with this? At the end of the day, our app is just a single app. We're just building an app within an operating system. That means that if one of these many features uses too many resources, such as memory, the whole app can be killed by the operating system. So we have to be extremely careful about how we write our code. I'm going to share with you a bunch of stories today of how we transition our company into one that cares about mobile as a first priority. I'm going to cover 2 main topics. The first one is coding at scale. What is this process like when you transition from having a handful of engineers writing your mobile app to more than 100 committers? And the second, releasing to the world. What is this process like, and what happens afterwards? Let's dive into coding at scale. As Tom mentioned, back a couple years ago, we used to have a centralized mobile team. We soon transitioned into having over 100 committers into the same code base. I'll be honest with you, this was a little scary, because very soon our build was broken pretty often. And even if you managed to build a whole app, which took a while, the app used to be unstable. It used to crash a lot. This was the version in master. So we had to spend a lot of time stabilizing and fixing all of these features before we released. We soon knew that we had to make some big foundational changes for this to work out. And we knew that we had to enforce 2 main things. The first one was enforce testing to avoid writing brittle code. And the second was focus on breaking the dependencies amongst the different teams. In other words, if I'm an engineer working on groups and the newsfeed is broken in master, I should not be blocked at that point. So what did we do? The foundation of our code base is really important. So we introduced the usage of dependency injection. For those who are not familiar with dependency injection, this is a design pattern. And the focus of it is to externally set dependencies aside from the implementation of the actual object. This encourages modularity as well as testability in the code. Let's look at an example. Let's say we're looking to write the code that fetches all the information necessary to render the newsfeed. To do this, we need some sort of helpers or dependencies. For example, we need a helper to make an HTTP request, another one to parse the JSON data, and another one to download the JPEGs that we want to render in the feed. What does this look like in code? Well, one way of writing the code is by just instantiating all of these dependencies inside the constructor. So right off the bat, there's a problem here. It's impossible to write a unit test. That HTTP request helper that you see probably needs access to the internet, and that doesn't work well with unit tests. The second problem is the series of dots that I have after the constructor. It's kind of a placeholder to tell you that these dependencies also need other dependencies. So suddenly, you're building this fetcher, and you have to build the dependencies of the dependencies, and it can get really hairy really quickly. So what does your code look like in general if you use dependency injection? Well, one difference is that instead of instantiating the dependencies within the constructor, we're going to specify them as parameters in the constructor itself. At this point, we can just say, to run a unit test, pass a fake object or a mock object into this class. Number two, we can use this code and pass it different dependencies, as long as these dependencies implement the agreed upon interfaces. And the last thing is, we do not need to build the dependencies of dependencies. Now, there's one more thing I want you to pay attention to, and this is this @inject annotation that I have in the code. What this is doing, it's a tag in Java, and it tells the framework, hey, whenever I need an object of the type fetch newsfeed method, look at this constructor and pass it these dependencies to create it. As consumers, we never have to call new in this object. So that was a pretty quick walkthrough dependency injection. And what I want you to get out of this is the importance of writing much more testable code. It's a lot easier to write unit tests using dependency injection. It also encourages code modularity because of all the separation. And at the end of the day is what helped us scale our code base from a handful of engineers into having more than 100 committers to it. Now, if you have written code using dependency injection, in particular in the context of Android, you probably have heard that performance is a big problem. So you might be curious as to how we addressed it. So let's try to understand the performance problem. Again, we're telling the framework, figure out these dependencies for me so that when I need them, I don't have to figure out where to get these objects and how to build them. So the step of dependency resolution is pretty crucial. There's one way to resolve these dependencies at runtime. But the problem, and the idea here is, we can have the framework go through each of these tags at the initialization time of the app and create all of these dependencies. Now, this is a little tricky because in the context of a mobile phone, this can take some non-trivial amount of time because this is done using reflection. So what do we do? A different way is to hardcode all of these dependencies at compile time so that they are all ready when you start your application. This is what we did internally, and this is what we used to ship our app in the last year and a half. If you guys are familiar, if you guys have used dependency injection, in particular in the context of Android, you probably have heard about Dagger, an open source library by Square. It uses the same idea of dependency resolution. But there's one more thing that we do. One of the things that we notice is that after shipping more and more code and writing a lot more injectable code, we noticed that our startup time was increasing, and we're trying to understand why. Well, it turns out that one implementation detail of compile time dependency resolution is the creation of a wrapper object around each injectable object. What it does is it tells the framework these are the dependencies for it. So in the context of a mobile phone, this every time we create a new instance, it takes between 100 and 200 microseconds. This, compounded by all of the classes that we had, was creating some non-trivial initialization time. One of our engineers had this idea of modifying the bytecode. The idea here is, once you compile your app, the dependencies are fixed. So he went at the Java bytecode level and modified the creation of these new providers to use static classes. We no longer needed to create these new objects, and suddenly we saw a big improvement in our startup time by 20%. So there's one more thing I want to cover before I wrap up this dependency injection. This is a screenshot of a diff I sent out for review a while back. I have blurred a bunch of our internal information here, but what I want you to focus on is the series of red and green squares. Every time we send out a diff for review, we kick off a series of asynchronous builds and unit test runs. The point of this is that by the time you come back to review your diff, you realize what you broke and what you didn't. As developers, we might think that whatever we're building is perfect and foolproof, but not realize that we're breaking something somewhere else in the app, just because of all the shared libraries that we use. So we can be assured that by the time we check in this code, we won't be breaking anything. So that was one of the advantages of modularizing everything and being able to write unit tests. The second story I want to share with you is about the importance of building good common APIs. One of the things that we noticed when we started writing our app on mobile was that for most features that we were building, we had to write all of the code necessary for fetching some data, storing it locally, and rendering on the phone. So we went on and learned how to write it. But then as we started developing more and more features, we realized that a bunch of the different product teams were building very similar verticals. Okay, well, so you may be wondering, why didn't you abstract the library? Well, the problem here lies in the heterogeneous nature of the data we're fetching. For instance, the messenger team probably cares about fetching user conversations, versus the events team probably cares about downloading all of the structured calendar information for the particular user. So there are all these slight differences that made this problem really hard to abstract. At some point, one very excited engineer thought, hey, I want to refactor our JSON step, our JSON parsing step. And this was common across the board in all of our fetching pipelines. But he soon realized to do this, he had to go through hundreds of call sites and make all of these changes. This was a little bit scary because he could be breaking existing functionality just because all of these verticals were implementing the similar idea but in a slightly different manner. So we were wondering, should it be really that hard to be doing a refactoring code like this? And the answer is no. What we do today is slightly different. Whenever a product engineer wants to fetch some data from our servers, they specify a small text, a small file that has text with the parameters that they want to actually fetch. They run scripts to generate 3 separate files. The first one, it's a Java class that makes the HTTP request, and it parameterizes it with the data that was given. The second one parses all of the JSON content and stores all of this information into plain Java objects. And finally, the last file stores all of this information locally on the device in a structured manner. We call the teams that work on these APIs product infrastructure teams. And they're really important, and their focus is to build all of the tools that the product teams need in order to make their job more efficient, and so that the product teams can focus on building the best experiences out for the users. So that's all I have in terms of the foundation of our code base. I want to switch gears now into our release process and what happens afterwards. Of course, when we write our features and we're ready for them to be shipped, we want to make sure that they work very well in all of the devices that run Facebook. In our case, this includes over 5,000 different Android device models due to Android fragmentation. To make sure that this is working properly, we have staged releases. The first one is employee dog food. And what's the point here? Every employee at Facebook that owns an Android phone gets to try the latest features using the freshest build of Facebook for Android. This is really cool because we get to play with really new stuff that hasn't come out, but at the same time, we will run into some bugs or bad user experiences. And when an employee runs into a frustrating experience, they get to use our Rage Shake feature. What is this? They get to, whenever they see a bug, they shake their phone in an enraged manner, just like this, and they get taken to a bug reporting flow. It's really important for us to close this loop and understand what is working and what is not working out there, so we can keep iterating, fixing bugs, and moving really fast. Gradually, after more iteration and more polish, we release our features into first our alpha test channel, which has over 100,000 testers, and then our beta test channel, where we have over 1 million beta testers. After more iterations, more polish, and more stabilization, we get to release to the world. So this process as a whole helps us identify a lot of the bugs that we weren't able to identify as with our fast connections or with our fast phones. We get to try it amongst different devices, across different, amongst the world as well. But even sometimes, after all of this testing, we will run into some issues, and we will see that we release a bug that is out in the world. And it's really important for us to be able to catch this bug and it's important for us to catch this bug, fix it, and move on. So let me tell you a story of something that actually happened live. We had a bug in our photo uploading flow last year. So when you if you want to build a progress indicator on Android, you can write code that looks like this. The %d is a placeholder for an integer. Say we want to show that 70% of the photos are uploaded. Because the % is a special character, in order to show the actual %, we need to escape it with 2 %. So this is pretty simple. In our localization step, one of our translators drop one of the % only in Danish, Finnish, and Polish. So this was really hard for us to catch internally. We didn't see this problem. Even in the beta channel, we only saw it 3 times. This was aggravated by the fact not only that this was happening in just these languages, but because this string was only used in gingerbread devices. So what happens to the user experience? This causes an exception, and the whole upload flow fails. We weren't able to see this internally, but when we released, we saw a huge spike in upload failures. In fact, more than 100,000 users were affected by this live bug. So, but the important thing here is that we were able to catch all of this while it was happening live. We were able to reproduce it and send a patch to it. Let me tell you a little bit more about the tools that we use to identify all of these issues. So, we need to understand how our app is doing once we release it. We have several sources of information. One of them is crash logs. The second one is bug reports, either by the rate shake of our employees or by external user reports. And the last one is just plain Google Play Store reviews. Whenever you get asked to rate an app and say how many stars you want to give to it, we can actually crawl all of that information in the form of text and make some sense out of it. All of this information is in the form of plain text. All of the snippets of information can be referring to one or many bugs, but it's really impossible for us to sift through them by hand. So what we need to do is we need to use our internal data analytics processing pipeline that we call Scuba, together with natural language processing technologies, in order to cluster and rank the top crashes and the top bugs that we actually see. This helps us understand how well our app is doing once we release it, as well as, in general, identify what is the next product direction that we should be following. I want you to take a look at this screenshot. Again, I have blurred a bunch of our internal information here, but this is the console that an engineer sees when they're working on a particular crash. On the left side, we have a full stack trace of the crash that is happening, already clustered by our algorithms. And on the right side, we have all of this aggregated information, such as the total number of crashes that are happening live, the affected users, what Android locales and app versions this is happening in. All of this information so that we can first identify how bad this problem is, how we can fix them so that we can actually release a much more stable app. At Facebook, we care a lot about building a very good, solid app. So we have focused full teams just to be working on tools that, like this, so we can triage our crashes. We also have a company-wide effort to lower our crash rate. In fact, in the last 6 months, we're able to reduce the crashes in our main app by 75%. So that's all I have for you guys today. If you guys are interested in learning more about our release process, I encourage you to stick around the talk after the session, which is on releasing and optimizing mobile apps for the world. And this is by Christian and Chuck. Thanks.
All right. Thank you, Jenny. So Jenny talked a lot about how different product teams come together and build out features in our main apps. But we also have a bunch of standalone apps that some of you may use. So we have an app called the Pages Manager mobile app. If you have a page for your business or an interest that you have fans that follow you, you can use that to keep track of things. Of course, we have our messenger experience, and I think a lot of you probably saw the talk by Luke Woods earlier on all the design work that went into making that a really world-class experience for messaging with your friends. And of course, in 2012, the Instagram team joined Facebook and are really focused on a photos experience, and have been doing a really great job there. Earlier this year in February, we released our latest standalone app, Paper for iOS. It's the first app as part of an initiative that we call Creative Labs. And we have several teams at Facebook that are building out focused, first-class mobile experiences that will take the form of standalone apps that we'll release over time. What the Paper team did is they took a really close, deep look at how people explore stories on Facebook, both in their news feed as well as from other content publishers in the Facebook ecosystem. And they built a really rich gestural experience of being able to navigate and read these stories that just feels simply amazing on a mobile device. And to talk about all of the engineering work that we had to do to make that possible, I'd like to introduce Scott.
Thanks, Tom. My name is Scott Goodson, and I'm the engineering manager for the Paper team. Before Facebook, I worked at Apple as engineer number 10 on the iPhone software team before the first iPhone came out, and helped to design the public SDK, as well as implement several of the first-party apps. After that, after about iOS 5, I went to a small startup company called Nest Computing to help build their iPhone app, and learned a lot about how small teams build products. The Paper team is a highly integrated group of individuals that are responsible for the product from the very earliest design concept through implementing a very polished version of that design vision, and then rolling out the app to users around the world. Indeed, we even choose the version numbering scheme. This is a very different model than the distributed engineering teams that construct the main Facebook apps. And we find that this is the best way to approach a completely new experience like Paper. And so that's why the Paper team has served as a model for Facebook Creative Labs, and we're sharing our learnings on how to structure such a team by replicating that around the company. Today I'd like to take you on a journey of 3 parts. And the first is to go into a little bit of detail on the history of Paper, most particularly how the design challenged the engineers to come up with new solutions. And the second is a deep technical dive into the particulars of one of those solutions. And the third, which I'm actually most excited to talk to you about today, is how you can use some of the very same principles in your own apps by a combination of open source releases we've recently made available, as well as other technical resources. When I started working on Paper, there was no code. In fact, it was just an idea, a philosophy of honoring the content. We had no ship date. If you look at a story like this, you can imagine that the person who made it took a fair amount of time to write a long piece of text, and we felt obligated to do the best we could to represent the content that they created. And for a long text post, that's not just showing more of the text, but making it possible to read the entire post with a single swipe up gesture without navigating to a different part of the app. We also observed that photos were becoming progressively higher resolution on mobile, yet apps were not showing them at any larger scale so you could appreciate this resolution. Fortunately for us, there was a great computer vision team ramping up at Facebook that we used to identify an appropriate center to do a full screen crop like this, to bring out a lot more detail in the photo and yet have it be in the most interesting place in the photograph. And of course, there are countless more story types like this event, which most of you probably would have just flown right by in your feed because it's not very prominent. Yet this is a wonderful opportunity to engage with your friends in person. And people take a lot of time to put together these kind of posts, so they deserve equal prominence. But where it really starts to get interesting is that our designers were the first that I've met to use these interactive prototyping tools that you heard Luke talk about earlier, if you learned about the Messenger redesign. In fact, they were the same people who were building and iterating on what those tools actually were. And this allowed them to build prototypes of things that we had no code for. And in fact, that we may not have even known how to build at all. And to share those ideas with engineers to really compel us to find new ways to implement these things. Here are a couple of the earliest interactive prototypes I saw. By this point, my enthusiasm for architecting a new user interface and a new app was starting to be overcome by worry. I had never seen an app in years of building apps that behaved like this, that reacted to users' gestures in such a fluid manner and reconfigured itself in an almost organic way, abiding by the laws of physics rather than the laws of software, which feel relatively contrived. The scaling effect on the left-hand side is one that affects all elements, and indeed, if you look at this in the production app, they scale at a different rate relative to each other, so they maximize they are the best representation in each size. And on the right, the composer is designed to be pixel identical to what you end up posting at every point as you're composing it. But our designers didn't stop there. The first time we ever saw the Tilt to Explore Photos feature was with this very demo. In fact, we just really hadn't even heard the idea of doing this before we were playing with it on a physical device and could experience what it would be like after we built it. So I was thinking, maybe we could get away with these 2 or 3 areas and we could kind of fudge it a little bit and we'd be okay. I got progressively more excited and more worried as I saw designs like this that made me understand that this type of interactivity was intended to be imbued in every part of the app and was a fundamental shift in the way that an app is intended to be perceived. That it should be a collection of interactable objects and be broken out of the traditional constraints of desktop software. Unfortunately, mobile SDKs make this really tough. They were not architected for this kind of thing, and in fact were very heavily optimized for individual tap gestures that then push a new view controller on the screen, and these type of animations that you can't interrupt, that are just to tell you about something that the app is doing, but they're not intended for your participation. They're just meant for you to watch. But iOS 7 and Paper are fully interactive and have a concept that's much closer to physical objects that can be in any state of transition, and you can grab something while it's moving and redirect it, or it takes into account the velocity of your gesture when you throw something. So we can't use something like core animation for this. But what exactly is harder about this? In iOS 6 and before, there was quite a bit of tolerance for main thread stalls. Like, if you tap a button, it's usually permissible to have about 100 milliseconds of delay before the actual action occurs. And also, static animations that move something across the screen were implemented in an out-of-process architecture that make them not subject to being stalled or skipped by blocking the main thread, even if you block the main thread for the entire duration of the animation. Neither of these things are true for newer style UIs like Paper. Continuous gestures like pans and pinches are everywhere, and dynamic animations that are governed by a physics engine need to run on every single frame. And because the system also needs time in each 16 millisecond frame, that means you only have about 5 milliseconds of runtime on a relatively slow mobile CPU, or you will drop frames. So the first challenge was to be able to do physics at all. And in an era before UIKit Dynamics, that was definitely a challenge. We've implemented this framework called POP that was just open source 2 days ago. I really encourage you to check it out. This was a huge piece of work, and I'm actually really proud of the API the team came up with to make it very similar to static animations, but you can add this element of dynamicism to them. But what I'd like to talk more about is performance. This is what Paper looked like when we used traditional app implementation techniques. There are just too many pieces of text. There are too many huge images. These Tilt to Explore images extend way off the screen and are much larger in size than the whole display buffer. And it became clear we had a really structural problem. POP allows us to get the sort of bounce effects and settling behavior that we wanted, but it did nothing for the performance problems. So let's explore a little bit in detail about the architecture behind iOS. It was designed in an era where single core processors were the only thing around, and in fact dual core processors seemed years away, and actually were. And also, this was at a time where mobile development was a new concept. And so to get more developers, a huge priority was placed on the simplicity of the API. This resulted in a very focused, single-threaded model where there's a thread considered the main thread where all touch events, all gestures are sent to be handled. And the most important thing to realize is that because physics simulating animations need to be interruptible and they need to be influenced directly by gestures, they too must be processed on the main thread or they will not behave predictably. So what actually causes a stall of the main thread, which we can't really tolerate in this new UI? One of the most common things is the laying out of text. Calculating where words will wrap and the shape of a paragraph and how tall the paragraph is actually quite computationally expensive. Rendering just about anything, including text, if you take a font specification with vectors and rasterize it into actual characters, especially on a retina display with very high resolution, again, this is very CPU intensive. Decoding images, whether they be PNG assets that are part of your actual app Chrome, or user content that are JPEGs, very expensive to decode. Drawing anything like a shadow or a border that may be part of your app UI is also pretty expensive. System objects, again, because the SDK was designed to be main thread centric, there are so many of them that even just creating them and manipulating them and destroying them very quickly adds up to a problem. So why can't we just optimize all of these things? That's a great idea, and you absolutely should do that. But what happens if your app still stutters after you've reached the long tail where it becomes much more difficult to get additional performance gains? Typically, you have no good options. You can make the design simpler, you can wait for newer hardware to come out, or you can ship a bad, suboptimal user experience. This is exactly where we found ourselves with Paper. So if we wanted to do something structurally different, here are the constraints. We want it to be smooth by default, so that without an engineer spending an extraordinary amount of time optimizing something, it is at least smooth. And so if they do not spend that time to optimize, then it might not load as quickly as ideal. And so that optimization is still valuable in making things show up faster, but it should not cause the UI to stutter. We wanted something fully generalized that applied not just to newsfeed, but could be used in timeline or the comment stream, everywhere in the app. And in terms of the system, an important constraint is that UIKit and core animation are not thread safe at all, so they'll crash if you use them off the main thread. But yet, we can't just rebuild UIKit. It's a massive framework, and it provides critical functionality like UI WebView or UI text field that would be infeasible to rebuild. So let's look at this in more detail. On iOS, everything that you see on screen is a CA layer. Even though core animation has no concept of touches, this is still true. UIKit provides an abstraction on top of it that's called UI View that adds features to layers, including gesture handling. And so we looked at this and thought, if core animation didn't have all of the features that UIKit wanted, and it extended it with this pattern, what if UIKit doesn't have all of the features we wanted? Can we just extend it in the same way? And that's exactly what we did. So instead of programming directly to views, we programmed to an intermediate concept called a node, which is a thread-safe API that we control. And it marshals interactions to the system objects to maximize performance. If you were here for the React talk, this is very conceptually similar to the virtual DOM. They're parallel concepts. This is not declarative, for example, but fundamentally abstracting away from system performance limitations has proven very successful for Facebook. So how does this solve the problems I mentioned earlier? For calculating the size of text, we can now dispatch to a background thread, and then we can create even a very deep hierarchy of elements. Previously with UIKit, or even core animation directly, this would simply crash, or it's at least prone to crashing. Then we can call layout, and that will recursively go through the whole tree, providing constraints all the way down, and you have your result. It really is this simple for a developer. What about rendering? Rendering is a much more general concept. But still, the system will call this method called display. This is actually in our implementation, so you would not have to implement a method like this. But the display method is called on the main thread. So instead of blocking the main thread, we just immediately dispatch to a background queue. Then we create a new graphics context, a buffer that we can draw anything into, just a space of pixels. And we call the node subclass and ask it to draw whatever it would like. There might be text, images, both, arbitrary graphics. And when that's done, we simply jump back to the main thread to set the contents on the layer because the layer is not thread safe. So these were the two most critical parts of this abstraction, but we quickly realized that there were other critical improvements that we could get out of a system like this that we didn't even realize in the beginning. In fact, we're still finding more of them today. I only have time to talk about the first three here, but they're some of the most important. If you look at this diagram, you can't help but think that the view feels a little bit like a middleman. And it turns out that there are many places in your application's view hierarchy where you don't need any of the features of UI view. If you imagine any of these boxes as a button, there's a label inside of the button. That label never needs to know when you tap on it because the button itself is detecting when you tap on any space in the button. So it turns out you don't need the features of UI view. And additionally, UI views are several times more expensive to create than layers. So we added a property to nodes that's simply called isLayerBacked. And when you enable that, it just does not create the view. And you lose event handling in that case. But for many places in the hierarchy, and in fact, this was about 50% of all views in paper, this works just fine and it is a significant optimization. Another one we call subtree precompositing. This is somewhat similar to should rasterize, which is a CA layer property, but it's much safer to use and much more practical. It's very convenient to build something like this link attachment out of separate elements that can be laid out, and so you can reuse the code to position things in different spaces. But it's much more efficient to create a single draw method that results in one buffer and one texture to provide to the GPU. So if you recognize that there's a part of your UI that can be drawn in this way, you can again enable a Boolean property on it, and you get a double win. This is like an extension of layer backing. We don't have to create either the views or the layers for that entire subtree, and it simply generates a single texture, like this. Even though in your programming model you have all of these separate layers that are represented as nodes. This is a huge optimization for the iPhone 4's very slow GPU. It's also a CPU optimization. Finally, concurrency is critical today because 80% of iOS devices are dual core. And of course, this has been all three of the last system-on-chip designs from Apple, and no doubt everyone to come will have at least 2 cores. Asynchronous operation is necessary for avoiding stutters in a UI, but concurrency allows you to radically speed up how quickly something will appear. The A7 processor is so fast that wasting even a percentage of one of its cores is a massive amount of performance to leave on the table. And we can parallelize layout and rendering, which are two of the most expensive things that an app does. Ironically, this even improves performance per watt and decreases power consumption because it allows the CPU to finish its work sooner and then go back to sleep and enter a low power state. So what are the technical takeaways here? One is to not always divide and conquer. This is a critical technique we're all very familiar with, but in cases like this, unifying your problem space and abstracting from there can be powerful. In fact, you will often find benefits that you didn't think of at the beginning. Another thing is to accept the challenge of ambitious designs. It's tempting to tell a designer that you can't build something, it's going to take too long. But if you agree that that is the right product, that it would be better if it could be built, spend at least a little bit more time thinking about it, and it might end up being the right trade-off to spend that extra time, because then you've increased your overall capabilities as a team and you can often reuse that work elsewhere. And of course, if you're doing that work, you need to be very careful not to reinvent the wheel, in this case UIKit, because that will slow you down. Since Mark started working on Facebook in a dorm room, we've been using open source software. Only since Facebook has scaled very significantly have we actually encountered the type of problems that, once solved, are useful to share back to the community. And we've started to do this on a mass scale from user interface engineering, front-end web, back-end servers, even hardware with the Open Compute project. But since the transition to mobile, it turns out that the entire industry is still catching up in open source frameworks on mobile. So I'm proud to say that we're trying to lead this charge with Paper, and we've already open sourced 6 projects just from Paper alone. And we intend to make this a trend for the organization overall. So I want to talk to you a little bit about these frameworks. If you go to this URL at the bottom, by the way, it's a group, but there's a post there where you can get direct URLs to everything. KVO stands for Key Value Observing. It's a very old API to get notifications for when your data model changes and you need to update your views. In fact, it's widely considered to be one of the worst APIs available from Apple. Yet it's very, very useful, and there is no other replacement for it that works in the same way. So we built KVO Controller, which brings it into the modern era by adding blocks and making it much more fault-tolerant in multi-threaded environments. And this project has been very popular, about 2,000 stars. There's a framework called Shimmer that gives you this nice loading effect that you can apply not just to text, but arbitrary layers as well. And we've seen about 3,000 stars for this project, so check it out. There's a framework we've made available called Tweaks that we use very, very heavily in building Paper that allows you to tune UI parameters, whether physics or colors or position, or even enable or disable entire features as you're prototyping them, that allow you to do things like check in to master a feature that you only want a few other people on your team to see, but you want to be able to collaborate on it and not worry as much about branching. So we found this very useful. And of course, there's the animation framework I mentioned earlier, which we just did a long blog post about to give you full details on how to use it. As opposed to UIKit Dynamics, you don't need to change your entire programming model to use POP. It's almost a line-for-line replacement of core animation or UI view animation APIs, but you get this kind of physical effect. And on the tools side, there's Origami, which the name is no accident. It relates to Paper because they've been built in parallel. But one of the coolest things about Origami is that once your designer has implemented a dynamic interaction in a prototypical form, you can take the exact same physics values and put them in your application, and the result will be identical. We've started to do engineering blog posts, only 2 so far, but more are planned. And so we want to give you a little bit more detailed overview in how we've approached these problems internally. And there are also Paper Tech Talks available that were performed just recently on 5 very detailed subjects ranging from new user experience implementations to architecting the what you see is what you get composer that can reconfigure itself dynamically and POP itself. And also this group, which you'll find at the URL earlier, is a place where we would invite questions about iOS or Paper or anything in general, these open source frameworks, to discuss with the team. But there's one more thing I wanted to share because it's been very highly requested. We're intending to open source the asynchronous user interface technology I discussed earlier. And in order to do this, we will need a fair number of beta testers to give us feedback on the API and help us get it all the way there. This will take several more weeks, but within a few weeks we should be open for beta. And if you'd like to talk to me about this, find me after at the open source desk. I hope you enjoyed all the talks today, and find us after if you have any questions. Thanks.
All right, that's awesome. Thank you very much, guys. We're a little short of time, so definitely try to catch these folks over at the table. We have one more session, which is going to be starting at 4:45 on how we launch and release the apps, and it's going to be a really good one. So look forward to seeing you all there. Thank you.